So today we're going to work with day 3, comparing multiple representations of functions. So what I'm going to do is I'm going to start with a graph, and let's talk about each of these functions. Okay, so how would you describe the graph of function A? Pardon me, how would you describe function A based on its graph? Well, we know that function A is going to be linear. Notice that we have a constant rate of change the whole way through. When we look at function B, we've got this U-shaped parabola. And remember, a parabola is the graph of a quadratic function. And then we look at C. Notice how it flattens. It starts sort of flattened out, but it grows rather quickly. C is going to be the graph of an exponential function. So that's what the graph of each function looks like. Now let's actually go through and answer some questions. Okay, which function has the largest x-intercept? Well, remember the x-intercept is where we touch the x-axis. So this is for function B. Here's an x-intercept for function B also. And then here's an x-intercept for function A. So it looks like function A has the greatest x-intercept. Which function has the largest y-intercept? Well, remember the y-intercept is where we touch the y-axis. Function C has a y-intercept here. So we travel along the y-axis. I don't see anything until we get here, and that is actually the y-intercept for function A. All right, so function A also has the largest y-intercept. So it has the largest x-intercept. It also has the largest y-intercept. All right, so now let's look at this next piece. Let's list the functions in order from smallest to biggest when x equals 2. All right, so let's find where x equals 2 on all of these. So here's where function B has x equals 2. Here function C has x equals 2. And here x equals 2 for function A. So smallest to largest, we go B, C, A. So this point, this point, this point. Function B has the smallest value, then function C, and then function A has the greatest. So we'll go from B to C to A. All right. List the functions in order from smallest to biggest when x equals 5. All right, so I'm actually going to have to decrease my scale here so that we can see this a little better. All right, so when x equals 5, let's start here. This is function C. When x equals 5, this is function A. When x equals 5, this point is part of function B. So we're going to go C, A, B. All right. Let's see what happens when x equals 7. So, whoa. Okay, so it looks like all of them, they are all the same value, which happens to be 3 at x equals 7. Okay. Well, now let's look at what happens when x equals 9. I'm going to get another color here. All right, so when x equals 9, let me focus here on the graph. When x equals 9, well, I've got function A here. I need to continue this down. So this will continue down to here somewhere. So that is function B. And we need to see what happens with function C. So function C is going to carry up to somewhere here. So it looks like we've got B, then A, then C. Okay? And then the last one asks us to list the functions in order from smallest to biggest when x equals 15. Well, x equals 15 is off of our graph. So notice function B had this downward trend. It'll be down here somewhere. Function A continues my line, and then function C is way up there. So it looks like as x gets larger, the upside down quadratic gives us the smallest value. Then the negative linear function gives us the next value. But our greatest value comes from the exponential function, function C. All right. Which functions have a positive rate of change throughout the entire graph? And let's go ahead and look at which functions have a negative rate of change. Okay. So as we look at this, we see that this is growing, growing, growing. So it looks like function C has a positive rate of change. Negative throughout, it looks like function A has a negative rate of change. And let me go ahead and read this question down here. Which graph has a rate of change that is negative and positive? Well, look at this one. That means it changes from increasing to decreasing or decreasing to increasing. This one has an increasing rate of change or a positive rate of change, then a negative rate of change. So function B goes from a positive rate of change into a negative rate of change. So let me remember these for the answers down here. So we said that function C has a positive rate of change throughout. Function A has a negative rate of change throughout. And then function B has a rate of change that is negative and positive. All right. Then it's going to ask me questions about rate of change and then one more question. So I think this is what I want to do. Let me sort of fold this. All right, so here we go. Which function has the largest rate of change from x equals 3 to x equals 5? Well, let's look at each of them. So let's look at function A. Function A is here. So function A, when x equals 3, is here. And then to where x equals 5 is here. So it looks like we'll go down 2 and then to the right 2. So function A goes from -2 to +2. So its rate of change is -1. All right, let's see what happens on function B. So on function B, my graph is here and it goes up to here. So we're going to go up 1, 2, 3, 4, and then we're going to go to the right 2. So function B has a rate of change with a rise of 4, and a run of 2. So that rate of change is 2. And now let's look at function C from x equals 3 to x equals 5. Well, x equals 3 is here. We're going to go up just a smidge to where x equals 5 here. So this is not quite half, maybe half of a half. We'll say 1/4, but then we go to the right 2. So function C has a rate of change of 1/4 divided by 2. Well, 1/2 of 1/4 is 1/8. So what's the largest rate of change? Well, it's function C. No, my bad. It's function B, the largest. That's this one. All right. Let's see what the rate of change is from x equals 7 to x equals 8. So once again, let's look at function A from 7 to 8. So we will go down down 1, and then to the right 1. So my rate of change, -1 divided by 1 is -1. And guess what? It should be, okay? Remember, this is a linear function. Because this is a linear function, the rate of change is going to be constant throughout. Keep that in mind because I do have a classwork question about that. All right, now let's look at function B. Function B, where x equals 7 is here, to where x equals 8 is here. So we're going to go down 1, 2, 3, 4, 5, and then we're going to go to the right 1. So my rate of change is -5 divided by 1, which is -5. All right. And now let's look at my last one. From where x equals 7 to where x equals 8, which is here. So we're going to go up 1, 2, 3, 4, 5, 6. And then we're going to go to the right 1. So 6 divided by 1 is 6. And so which one of these has the greatest rate of change on the interval 7 to 8? Well, 6 is larger than all the others. So function C has the largest rate of change. And you'll learn that once we go further away from where they meet, C will always have the largest rate of change. Which function will eventually exceed the others? Well, that's the exponential. Okay, always. The exponential function will always exceed the others, as long as they're all increasing or decreasing or whatever. Okay? All right, so that's how we compare graphs of functions. So we're going to look at values. We'll look at rates of change. We'll look at when one exceeds the other. So now let's look at a comparison of different representations. So you'll notice here we've got a graph to describe f of x. We've got a table to describe g of x. So the first thing we have to do, the first thing I want to do is notice that this is linear. And this one I don't know, but I do know that when I add 2 here repeatedly to get to the next y, well, that tells me that this is also linear. Okay? The first thing I have to do is write an equation for each representation. Well, the way you write an equation for a linear expression is y equals mx plus b. So my y-intercept is here at 8. And then my slope is my rise over my run, so I'll pick 2 other points. We go down 2 to the right 1, so my slope is -2. So this function is -2x plus 8. Now look here, g of x, I should be saying g of x equals mx plus b, but I'm trying to maintain some irregular or wrong consistency. So here my slope is my rate of change, which is 2. My y-intercept, remember, is the value of y when x equals 0. So my y-intercept is -6. So g of x equals 2x minus 6. All right, which function has the smaller rate of change? Well, they have the same rate of change because they're changing differently, but since this one is actually going more negative, we'll go with this function because -2 is less than 2. I think that's what they're trying to get to, but we'll save that conversation for another day. All right, let's look at the next one. Now we're dealing with a table versus a graph, just like up there, but we've got a different function. I noticed that this one is quadratic because it's a parabola. I notice here that we have repeated values here and here. And then we have the same thing here and here. So it looks like we've got a quadratic here as well. Which quadratic value has the smaller minimum value? Well, my smallest minimum value is here because remember, this thing is going to sink down and work its way back up. So -9 is my smallest minimum value for f of x. F of x is min, or we should say the min of f of x equals -9. Look here, this minimum value is at my vertex here. So this is at, let me just write out my vertex. And this one is 1, -9. And then the minimum of g of x is -8. So f of x has the smaller min. All right. So for B, which quadratic function has the bigger y-intercept? Well, on a graph, you can pick out the y-intercept. Okay. The y-intercept here, oh dear, is going to be up here somewhere. Okay. So g of x has a positive y-intercept. F of x has what? Well, in a table, the y-intercept is where x equals 0. Okay. That's where x equals 0. So which one has the bigger y-intercept? G of x has the bigger y-intercept because any smaller or any positive number is greater than any negative number. Or just for this particular instance. Oh, good grief. This y-intercept is -8. Dude, let me start over. The y-intercept for f of x is -8 because that's where x equals 0. So the y-intercept is -8. So if this y-intercept is -8 and this y-intercept is positive, g of x has a bigger y-intercept because any positive number is greater than -8. Good grief, I messed that up so much, and I'm sorry. All right, and now we have to name the x-intercepts for each function. Well, for f of x, look where y equals 0. So that is here. That's an x-intercept. And, oh, wait a second now. I don't see, I do not see where we get 0 anywhere else. But I do notice something. Okay, here's what I notice. If I follow this pattern, we've got -9, and the two numbers surrounding it are -8. The two numbers surrounding those are -5. So the next two numbers are 0. So this one should be 0. So I'm actually going to fill in this missing value. And what is its corresponding x-coordinate? Well, let's see. We go from -4 to -3 to -2, -1, 0, 1. So I bet this corresponding x-coordinate will be 2. So this is my x-intercept. So my x-intercepts are -4 and 2. And now for my graph here for g of x. Well, here is an x-intercept. It's just greater than 1. So I think I'm going to call that 1.1 or 1.2. And then the other one is here, just before 7. So I'm going to call that 6.8. All right? So that's how we compare two different functions. All right. So far, so good? Okay. So now we've sort of looked at the background of a graph. We've looked at comparing multiple representations of a function. Now I want to dig deep into maybe some end of course test type questions. So I look here at this first one. A table of values is shown for f of x and g of x. Which statement compares the graphs of f of x and g of x? So they're giving you tables, but they're going to ask about the graph. So let's see what happens here. The graph of f of x always exceeds the graph of g of x over the interval 0 to 5. Well, let's see. Is 0 greater than -2? Yes. Is 1 greater than -1? Yes. So far, so good. Is 4 greater than 1? Yes. 9 is greater than 5. 16 is greater than 13. But, oh dear, 25 is less than 29. So this is not true. Okay, it exceeds up to the interval 0, 4, but not on the interval 0, 5. And always is a big deal in math. That means it has to be true every single time, and it's not. The graph of g of x always exceeds the graph of f of x over the interval? Well, no, because for the longest, f of x was greater. So we know that part B is not true. Okay, let's see if C is true. The graph of g of x exceeds the graph of f of x over the interval 0, 4. Right away, I can tell you no. The graphs intersect at a point, and then the graph of f of x exceeds. No, the graph of f of x exceeds first, so it's not that one. The graph of f of x exceeds g of x over the interval 0, 4. Yes. The graphs must intersect at a point. How would you know that, Robideer? Well, look at what happened on this one. Remember here, once you meet at some point, you have the same y values. Well, then suddenly your order of y values may change. So in order for one to overcome the other or exceed the other, they have to meet at some point. So this is true. The graphs meet at some point between 4 and 5. That's true. And then g of x will exceed afterwards. That's true. So the correct choice is D. So this requires a lot of reading on your part. So make sure you don't just gloss over it. I have a bad habit of doing that. Make sure you don't fall into that trap. All right, number 5, my bad. Which statement is true about the graphs of exponential functions? The graphs of exponential functions never exceed the graph of linear and quadratic. That's false, because we actually saw that in this function. They were sort of leading the pack for a while, like while the exponential was laying low. Okay. The graph of exponential functions always exceed? No, look at the last graph we just did. It doesn't always exceed. The graph of exponential functions eventually exceed the graphs of linear and quadratic? Yes. This one, the graphs of exponential gradually exceed linear but not quadratic? No, that's not the case. Because even if you've got some crazy long super quadratic and you've got an exponential that's sort of here and for the longest, it's just laying low. Eventually, it's going to take over and it'll start to get taller much faster than what will happen there. All right, and now our last one. Which statement best describes the comparison of the function values? Well, notice now we've got two tables sort of all put together with one x value. So let's see. Let's notice what happens here. 0 is greater than -10. 2 is greater than -9. 4 is greater than -6. 6 is greater than -1. 8 is greater than 6. So the values of f of x will always exceed the value. Well, that's what looks like happens here, but let's hold off on that one for a second. The values of g of x will always exceed f of x? No, because here are 5 instances where it did not. The values of f of x exceed over the interval 0 to 5? No, we're only going to 4. But now that you mention it, I should introduce 5 because I see it here in a choice and I see it here in a choice. So when x equals 5, this pattern says that f of 5 is going to be 10, right? Because we're adding 2 as we go, and that's how we get our next value. So 8 plus 2 is 10. Well, let's see what happens here. Negative 10 to negative 9 adds 1. Negative 9 to negative 6 adds 3. Negative 6 to negative 1, you get that by adding 5. To get from negative 1 to 6, you add 7. Okay, I see a pattern. Plus 1, plus 3, plus 5, plus 7. So to get the next term, we must add 9. 6 plus 9 is 15. And oh my goodness, look what just happened. When x equals 5, f of 5 is less than f of g of 5. So I think we can throw out this always now because of that. The values of f of x exceed the value of g of x over the interval 0 to 5? No. It only exceeds, it exceeds on 0 to 4. The values of g of x begin to exceed the values of f of x within the interval? Yeah, that's where g of x, and it's only going to get greater because then we'll have 10, 12, 14, 16. Then we'll have 15 plus 11, 26 plus 13, plus 15, plus 17. These could be wrong. I'm just, mental math is not good for me today. So it looks like D is correct. So that's how we compare. We can compare values in tables and we can compare their behavior. We can look at what happens or draw conclusions about graphs. If we have information about a table, we can draw conclusions about graphs. And that goes back to graphs and tables. And that goes back to comparing functions. And that's what this lesson was all about.